All right, the focus of this video is going to be linear approximation, also known as linearization if you're lazy and you want to swish the words together. And then we'll do probably differentials in the second video, and then we'll do Newton's method, which is an optional topic. Feel free to skip the Newton's method if you want. It's not on the AP exam. It's just kind of an extra bonus little thing. We'll probably just do that in this third separate video. But linear approximation, using a tangent line to approximate a more complicated function, like a curve. Okay, so let's go for it. First example, where I'm going to read it. It says a tangent line to a curve gives us a useful way to approximate a value on the curve. We usually write our equations in the tangent line in point-slope form, right? We know that. We've been doing that for a while. And then that means for any specific point, right, it's going to give us the x value. Here it says their x value is a, so at x equals a, I know in order to get the y-coordinate, all you'd have to do is plug the a in to the original function. So f of a, that just means the y value, which comes from plugging in your given x into the original. And then I know the m value, the slope of the graph at that point, aka the instantaneous rate of change, aka the derivative. That's going to come from taking the derivative of your function and then plugging your a value into the derivative. So this is just your point-slope form. It gives us the x value. And then to get the y value, you take your a, your given x value, you plug it into the original. And then to get your m, you would take your given x value and you'd plug it in to the derivative. Now keep in mind, these three should be numbers. That's a derivative value, not the whole derivative function. So it's the derivative having been plugged in, having been evaluated. It's not the whole derivative equation. Okay, let's go for it. Given f of x equals x squared, write the equation of the tangent line to the curve at x equals 1. Let's draw a picture, just because I think that always kind of helps. Sound effects make it better. We'll say here's the point 1, and I know just from my math skills, the y-coordinate is going to be at the point 1, 1. So we'll call the curve f, and then we'll refer to the tangent line as y. Just so we can differentiate between the two. Okay, so write the equation to the tangent line to f at x equals 1. So here that tangent line is going to touch, and then remember, tangent means it would just be parallel at that point. So it's just going to touch, and then it's going to graze, and then go on its merry way. So here is, in blue, I'm going to call y the tangent line. And it wants us to get the equation in point-slope form of that tangent line. We'll probably actually switch this one so that it's slope-intercept, but most of the time we care mostly about point-slope, and we always start with point-slope form. Okay, so here we go, part A. We got y minus y1 equals m x minus x1. There's my setup for my point-slope form. The question gave me the x value. How wonderful. To get the y value, what you would do is take the x and plug it in to the original. 1 squared is 1. I kind of knew that coordinate point was going to be 1, 1. But how you got the y value was you take your x, plug it into the original. That gets you the y coordinate. Okay, now I need to get the m. So that's going to mean take the derivative and plug in your x value into the derivative. Well, here this derivative is pretty simple. It's just 2x. So that means my derivative specifically at 1, right? The slope of the curve at this point, which is, since it's parallel to the tangent line, which is the same value, right? The slope of that tangent line never changes all the way on that tangent line. The slope's always the same. And then at this one specific point on the curve, the slope is going to match. Okay, so here the derivative at 1, 2 times 1 is just 2. So I know the slope of this curve is different at different points, right? Sometimes the slope is 0, sometimes it's negative, sometimes it's positive. But right at this point, we found that the slope of the curve was 2, which means the slope of this tangent line is also always going to be 2. So there we go. We can plug it in. And then that's pretty nice. If you want to leave that as your answer for part A, that's fine, right? If the question just says, give me the equation of the tangent line, point-slope form, something like this, is what you would want to stop at. However, when we're doing linear approximation, when we're going to be using this tangent line to do something, a lot of the times it's more useful to go ahead and just do the rest of the terms, do the rest of the steps, and get it into y equals. Okay, so I'm just going to move the 1 over. I'm not going to bother distributing the 2. That doesn't make any difference. I'm just going to take this 1 and add it over. So y is going to be equal to 2x minus 1 plus 1. And if you wanted to box this as your answer to part A, you could, but again, point slope form is fine. It's just when you're going to be using that tangent line to do something, it's going to be easier if it's in y equals. Okay, let's look at part B. Right, part A is done. Use my answer to A, so use this equation of the tangent line to find an approximation for f of 1.01. Okay, so let's think about this, right? 1.01, that would be slightly. This is not going to be to scale. That's okay. But 1.01 would be slightly to the right of 1, right? I'm kind of just making this diagram a little bit more zoomed in for dramatic effect. But 1.01 would be a point slightly to the right. The parabola would have a point at that specific height, right? For that given x value, the parabola is going to have a point on the curve. And what we're trying to do is figure out, okay, what is f of, come on, pencil, 1.01. Okay, so remember, f is the curve, y is the parabola. So what we're trying to do is figure out, okay, based on this tangent line, how can I somehow get a good estimation for where this point on the function is? Yeah, that's kind of the whole idea, approximating where that function is. Now, I know, since I have the equation for this function, x squared, I could find this value exactly, and we're going to in part C. But the idea is that even though this particular example is an easy function, it's an easy curve, in general, I may see stuff in the future that's a lot more complicated than just x squared. And the idea behind linear approximation is that you can use a straight line, and straight line functions, at most are going to have multiplication, maybe division, and then maybe addition or subtraction. Everything with a linear function is always just those basic operations. And I know I could always do those basic operations by hand. This curve happens to also be something we can do by hand. But this is just kind of the simplest example. Later on, you may see functions that are a lot more complicated. And the idea is I can use the straight line, the simple linear function, which I can always do by hand. I can use that as an approximation for the curve, which sometimes I can do by hand, but a lot of the times maybe not so much. Okay, so we're trying to find the approximation for this true function value. And what we're going to do is instead look at the point on the tangent line, right? That tangent line is going to end up being underneath the true function value. So I'm going to call this y of 1.01, noting that, hey, at this new x value, the tangent line is not the same point. It's not the same value as the function. But those 2 points are pretty close together. We call the gap between those 2 points the error. We don't really have to concern ourselves too much about error, but it's going to come up for us in the part D. Anyways, we're going to use the tangent line. We're going to figure out what this y-coordinate is to approximate the true function value. All right, let us go for it. So instead of using the curve, which if for this simple example, I could do by hand, but we're going to approximate the curve by using the linear function, which you would always be able to do by hand. So y of 1.01, I'm plugging in my new x value into my linear function for the tangent line. Whew. Oops, I need to minus the 1, don't I? Silly Mr. Bell. Okay, so this one we could do by hand, right? It's not too bad. 1.01 minus 1 would be 0.01. 2 times 0.01 would be 0.02. And then 0.02 plus 1, I know that point on the tangent line would end up being at 1.02. So this value is 1.02, right? It's slightly above 1. Of course, this diagram is not to scale. That's okay. So I know the tangent line is at this specific point, right? This y value is exactly equal to 1.02. That means my function, right? My function at this new value is going to be about 1.02. Okay, the tangent line is, so you could put y equals that number, but we're using that tangent line to approximate the true function value. So the tangent line is that number, which means your true function value, right? I still don't know what that point is yet, but it's going to be something pretty close to 1.02. So we're using the tangent line to approximate where the function is. Okay, so we're done with part B. Part C says, now find that actual function value. Find it exactly. Okay, so f of 1.01, that would just be 1.01 squared, which we could do this by hand, right? I could do 1.01, 1.01. We know how to do multiplication by hand. At least you should. Hopefully that was like elementary school. So I could do this by hand. In general, these curves, these more complicated functions, sometimes they won't be able to be done by hand. This is the easiest curve we could kind of come up with, just for the sake of a simple example. The idea, though, is I can always do the linear function by hand because it's multiplication, division, addition, or subtraction. All of those I can always do by hand. This curve happens to also be something I can do by hand. But later on, you may see stuff that's not so easy, right? So the idea is I can approximate this function by using the much easier equation, the straight function, the straight linear function. All right, so multiply this out, right? You'd end up getting 1.0201. So that is your exact function value, right? F of 1.01 is exactly equal to 1.0201. Oh my gosh, this pencil is going to be the end of me this year. Okay, so this true function value, right, the point on the curve, it's 1.0201. We got part C done. Now, was my point from the tangent line, is that pretty close to where that true function value is? Are these two numbers close together? Yes, they're very close together. They're not the exact same. Remember, I estimated where this point on the curve was by using the y value from the point on the linear function. But look, my estimation was pretty darn close to where that true function was. So again, you can approximate the more complicated thing, the curve, by using something that we can always do by hand. And then typically, those two values aren't going to be too far. So typically, we can get a good approximation. All right, last part of this. It says find the error. Here we go. Error. It's just going to be the magnitude, right? So you're going to take the absolute value of your exact solution minus your approximation. Right, so it's the difference. It's the size and the gap. Take this number minus this number, and then we're really not going to care if that subtraction gives you a plus or a minus result. We just want to know how big is the gap between those 2 points. So even if you were to switch these two, it doesn't matter because when you take the absolute value, you would get the positive number anyways. So let us go for it. 1.0201 minus 1.02. So the error, it's the gap between where the exact true function value is versus where my tangent line approximation was. It's just the size and the gap between those two, which here it looks like it's just going to be 0.0001. It's a pretty small error, right? My approximation was a very good approximation, which is pretty nice, right? Conceptually, what we just did was we took this curve, which for this question, we could have done by hand, right? Could have. But in the future, maybe those functions are too hard for us to do by hand. But I took that curve and I approximated where that y value was using a tangent line, which is something I can always do by hand. Okay, hopefully that makes sense. Using a straight line, linear function, something easy to approximate a curve, a stranger function, something that isn't necessarily always able to be done by hand. And then, of course, we have an approximation, so we're always going to be a little bit concerned with the error. How good is my approximation? How far off was it from the exact function value? Okay, let's move to the next one, and then we'll end this video. Application. Use a tangent line approximation, aka use linearization, to approximate the value of the cube root of 127. To do this, we're going to let the curve, the function f, we're going to let that be the cube root function, x to the 1/3 power, and then we're going to kind of build the equation for my tangent line by choosing a perfect cube close to 127, and then we're going to build my tangent line at that value. All right, so let's think about the picture for this one also. Okay, your cube root function looks something more or less like this. It also goes in the negative direction. So there you have it, right? There's your curve. Again, this is definitely not going to be to scale. Who cares? We want to know what the cube root of 127 is. So I kind of want to know exactly on the curve, where is that function value going to be? I want, what is f of 127? The problem is, I can't do the cube root of 127 by hand, right? You could guess and check, and you could be like, okay, I kind of know what it's going to be close to. And then I could just take that x value, multiply it out the 3 times, and then be like, okay, I'm not quite there. So then I could guess a little bit bigger or a little bit smaller. There's no algebraic or arithmetic way to solve this, right? That is a curved function, something that we can't necessarily solve by hand, because there's the quadratic formula for solving quadratics, but there's not really this cubic function for us to use and to plug in and to actually mathematically compute what a cube root is. But if I can somehow draw a tangent line, I can then use that very easy linear tangent line equation to get a good approximation for this cube root. All right, so let's think. A perfect cube close to 127. How about 125? Right, 125 is going to be pretty close. And I know 125 is nice because the cube root, right, we're going to use 125 because the cube root of 125 is 5. Right, so this y value for this point is going to be 5. Now, I know 127, it's a little bit bigger than 125, so I'm anticipating that the cube root of 127, it's probably going to be a little bit bigger than 5. But how we get it without guessing and checking? Well, we would use this tangent line process. Okay, so here we're going to set our function equal to the cube root, which I'm going to just rewrite it as x to the 1/3. And then we're going to have an x value. So our x value was 125. And I know f of 125 was 5. We just did that right here. Okay, so now I want the equation for the tangent line that hits at 125. Oops, there's kind of a little bit curved. That's okay. Here's y, the equation of the tangent line. And then the idea is, hey, this blue tangent line, I can look at the y value on the tangent line, which is something I am going to be able to do by hand. I'm going to use that y value on your tangent line, y of 127. And that's going to be a decent approximation for the curve, something I can't do by hand, because the gap between those 2 points, the error, it's pretty small. So let's get the equation of this blue tangent line. Right? If it says use a tangent line, the first thing you need is the equation of the tangent line. And then we're going to use it to approximate the function value. All right, so y minus the y coordinate, we're using the tangent line off of this point. Y minus 5 equals, I need to get the m value, x minus 125. Okay, so we need the derivative, and then I'm going to need to plug in 125 into the derivative. So here, let's go for it. You'd have 1/3 x to the negative 2/3, which means you'd have a 1/3x to the 2/3, right? There's your derivative. And then would I plug in 5 or would I plug in 125? Well, think about it. The x values are the bigger numbers, and then the y values are the smaller ones, right? Because your function cube roots the stuff, and it makes it smaller. So then here I would need to plug in 125, because that's the point where I'm building this tangent line off of. So I'd have 1/3, 125 to the 2/3 power. Okay, now there's two ways to do this rational exponent. You can take the 125 and then you can square it, which is going to give you a pretty big number, and then you can try to take the cube root of that really big number. Have fun doing that, right? That's not very easy. Or what you could do is take the 125. You can do the root first, do the bottom part of the exponent, and then that's going to keep your number smaller. And then once you keep the number smaller, then you could square that smaller number. So either way, you could square it, then cube root, or you could cube root, and then you could square it. Either way is fine. I'm going to do the bottom power first because that's going to keep the values a little bit more manageable. So here we go. 125. The cube root of it would be 5. And then 5 squared would be 25. So all of this stuff, 125 to the 2/3 power, That's equal to 25. Again, do the root first, which gives you 5. Then square it, which is 25. And then 25 times 3 is 75. So I'm going to end up getting that the slope of that curve at this point, aka the slope of the tangent line, it's 1 over 75. So again, I plugged in my x value to the original function. Here's your x value. Plug in it to get the y coordinate. Then you plug in the x value into the derivative to get the slope. And then let's get it to y equals. So I've got 5 plus 1/75 x minus 125. So here's your equation of that tangent line. Now what I want to do is figure out where is the tangent line at 127. Figure out what that y value is, and then that's going to be an approximation. It's going to be a guess for where that real function value is. Okay, so let's plug it in. Y of 127. Now I'm using the value that I was trying to approximate. 5 plus 1 over 75, 127 minus 125. Let's see. Now this linear function, is it something that we could do by hand? Yes, it's got multiplication, really it's got division, it's got subtraction, and it's got addition. The linear function, the tangent line, you're always able to do by hand, whereas the curve, you're not able to always do it. On the first example, yeah, you could have taken that x squared, you could have done that by hand. But for other curves, like the cube root and like many other curves, it's not something that you can do by hand. The idea, though, is I can use this linear function to approximate the more complicated equation, and then it's going to give you a pretty good guess. Okay, so here we go. 127 minus 125, that's 2. So I got 5 plus 2/75. Now, could I convert this to a decimal? Could I do 2 divided by 75? Yeah, right, it's going to go in 0 times, even goes in 0 times there. And then you could do the division, and you could figure out what that decimal is. I'm going to skip some. I'm going to not do that just because I'm a little bit lazy and I want to make this video a little bit shorter. Could I do this division by hand? Yes. Am I going to right now? No, right? But I could do this division, and then I could take that whatever decimal, then I could add it to 5. But just for the sake of time, this decimal, when you do 2, it's not 7.5, it should be 75. When I take 2 and I divide it by 75, it would end up giving you a decimal that's 0.02666, and it's just going to be repeating, right? So just pretend I did the division, which I could have done. I'm just skipping it for now. It gives me that decimal 0.026666666. It just keeps repeating. So then I could take 5 plus that decimal, and I could figure out my tangent line value is 5.026, which means the function value, right? So I know this point right here, the tangent line, it's at 5.026 repeating, which means that true function value is probably going to be pretty darn close to 5.026, right? It's probably going to be a little bit less, right? Since our diagram, it looks like the tangent line ends up above the true function value. I'm thinking this real function value is probably a little bit less. But that's okay. Therefore, my true function value is going to be about 5.026. Remember, the tangent line is equal. That means the function is about. So that means the cube root of 127 is going to be about 5.026. So using a tangent line to get a pretty good approximation for something that we cannot do mathematically by hand. Okay, if you're curious, use your calculator. The cube root of 127 is 5.0265. So my estimation, and then that true function value, 0.0265. Remember, that was 6666, so on and so forth. So the true function value, I think that might terminate, or it goes longer. I don't really remember. All I have on my answer key is those 4 decimals. But the true function value and my approximation, they ended up being very, very, very close together, right? That's your exact value, which we would have to use the calculator to find, but the approximation, which I could have done, right? All of that I could have done without a calculator. Wouldn't be very fun to do the division, but we could do it by hand. And then the error involved with this estimation, if I were to take this exact minus this approximation, the error that's involved is only 0.000141. Right, so that's just a little extra bonus. I don't think this one asked us about the error. But just keep in mind, when I'm using this linear function, this tangent line, something we can always do by hand, when I'm using it to approximate the curve, which I may be able to do by hand or maybe not, there's always going to be some element of error because you don't have the exact value. What you have is an approximation, but hopefully that approximation is a very good one and you have a small error. Okay, so linear approximation, using a straight line to approximate a curve, something that's more complicated. The straight line, the equation of the tangent line, we can always do by hand because at most it has addition, subtraction, multiplication, and division. All of those things we can do by hand without a calculator. Using that straight line to approximate a curve, which we probably won't be able to do without a calculator. Pretty neat little concept. I don't think these questions are super easy, but they could be much worse.